Okay, I hope this is okay for everybody. And okay, so 2.2. All right. So 2.2, and today is the 20th. Okay, so last time we were developing the governing equation for pressure variation, essentially Newton's second law, for static fluid, but also more generally, we could consider an accelerating body of fluid as long as there's no relative motion within the fluid, there are no shear stresses. And so once we get our governing equation, then we will first consider the case of a static fluid and determine the pressure variation in, first, the case of an incompressible fluid where the density is assumed constant, and then considering that density may vary. And the particular example or application of this would be to evaluate the pressure variation in the atmosphere. And so we'll see how the standard atmosphere values are determined. And then, so maybe I can finish that in this first session, and then the next session, pressure measurement, and in particular manometry. So we'll see how far we get. And so let's see, your first homework is due tomorrow by midnight. So I will have a second homework on the fluid statics. Okay, I think that was it for general announcements. So let's see, where were we? Okay, so we're considering a small fluid element, a cubical fluid element, in some body of fluid, and the objective is to determine the spatial pressure distribution, P of x, y, z, at any point in this body of fluid, and we're considering Cartesian coordinates. So we've got the cubical fluid element of sides delta x, delta y, delta z, and we're considering the net resultant force on this fluid element using Newton's second law. And the fluid element has a mass of delta m and then acceleration a. Okay, so we in general will consider all components, x, y, z components of the resultant force, and as I mentioned, in general, there are two types of forces: body forces, surface forces. Surface forces due to pressure. The only body force we're considering is due to the fact that we have a gravitational, the fluid is in a gravitational field. So basically the weight of the fluid. So we started off considering the surface forces associated with pressure. And we already had discussed that, so we know that force due to pressure, we evaluate the pressure at an area, and the resultant force would be the pressure across that surface area times the differential area, always acting towards the area as described by our expression here. And so the delta F would be a minus P differential area. Okay? And to evaluate the pressure at each of these areas, remember, we're assuming that the pressure continuously varies in this space. So there's going to be a variation in the pressure, and that we're going to account for or determine by applying Taylor series expansion and only taking the first derivative term, neglecting higher order terms. So we did that. So we evaluated the pressure. So considering the variation in the y direction, we evaluated that the pressure at y minus delta y over 2, which would be this surface here, a distance y minus delta y over 2, and then the pressure here at this location at a distance y plus delta y over 2. And so using the Taylor series expansion, we obtained these expressions. Okay, so the value of the pressure is expressed in terms of the pressure at XYZ, which was at point O, the center of the fluid element. And then we take each of these pressures and multiply by the differential area. And we found that the first term pressure cancels out, and these two add, so we get this expression for the net surface force in the y direction. And then we do that in the x and the z directions in a similar manner. So the net surface force in the x direction was this. The net surface force in the z direction, this. And then the vector, the surface force vector, would be given by the x, y, z components. And we now see, or saw, this is where we ended, that we have the net surface force expressed in terms of the derivative of the pressure, or in general, the pressure gradient, which is a vector, which is given exactly by this term in the parentheses. So we can write in shorthand or in a concise manner as minus grad P, or del P, and then the areas, each of the areas was also multiplied by this term. So each term is multiplied by delta x, delta y, delta z, which is actually the differential volume. So that's the net surface force. Now, very simple to evaluate the net body force. And so that's just the weight. So the differential weight is delta m times the gravitational acceleration. Mass is given by the density times the differential volume. So we can write this, the weight, express the weight in this way. Okay? And so the vector will be, the direction will be indicated by g. So we just write g as the vector. Okay, so then we go back to our general Newton's second law. In this guy here, we can again just express delta m in terms of the density, delta v. Okay, and that's the acceleration term on the right-hand side. This resultant force is the sum of the surface force plus the body force. So we can substitute in here using this expression and this. And then, of course, we can divide out by the differential volume. And so then we get minus del P plus rho G is equal to rho A. This is a vector equation. It is the general equation of motion because we can still consider fluid, the body of fluid, moving, as long as the motion in the fluid, there is no relative motion. So the body of fluid moves as a whole. Okay? So that's a key assumption that we made in our derivation. So the implication is no shear stresses. Otherwise, more generally, we would have to account for shear stresses as included in the surface forces, which we'll do when we do fluid dynamics differential analysis in Chapter 6. Okay? Okay, so, but here, no shear stresses. So we can solve for del P, the gradient of pressure, because remember, what we want to know is the pressure variation in the fluid. And then that is equal to rho G minus A. So the net resultant vector here would give the direction of grad P. Okay, so that's the general equation. And we can go back to this general form when we consider rigid body motion of fluid. But for now, and more significantly for our purposes, we're going to consider hydrostatics. So there, the fluid is at rest. The acceleration is 0. So this is the general equation for hydrostatics, getting the pressure variation in a fluid at rest. Now, we usually use Cartesian coordinates, and so we want to know how the pressure varies with elevation. So then Z, we usually choose Z as the coordinate, positive upwards for elevation. And so then the gravity vector would be pointing downwards. So we can then express the G vector as magnitude G with the direction minus K. Okay? So we can write that down. And now to apply this equation, we consider the component, each of the components. So the component of this equation in the x direction, x component of grad P is partial P partial x. And then here, there is no x component of the gravity, so it's 0. And then same with y component. So partial P partial y is 0. And then this is going to appear in the z component. So partial P partial z equal minus rho g, which, if you recall, remember, density is mass per unit volume. Mass times gravity is weight. So rho g is gamma, which we said and is defined as the specific weight, a fluid property related to density. Okay? So we can simplify by expressing this in terms of gamma, but I like to keep it explicitly in terms of rho g so that one easily remembers what we've got here. Okay, so now this is because there is no variation of pressure in the x or y direction. Only in the z direction, we can change the partial derivative to an ordinary differential. So dp dz equal minus rho g. So remember then that in a body of fluid at rest, at the same elevation, okay, there is no pressure variation. Okay, so no pressure variation in the horizontal. Okay, so then to get the actual pressure distribution or pressure variation in the z direction, we just integrate. Okay, so we can integrate from any two z values or from some reference value. But when we do this, then we have the integral of rho g dz. Okay? So to do the integration, we need to know how the density varies with z and how gravity varies with z. Okay? So first case. Now, actually, where do I discuss? I guess I don't have any comments here, but at this point, rather than this, maybe just add a note saying typically for typical applications, we assume gravity is constant, which we've already done maybe in our basic analyses. Even if we go up in the atmosphere, up to, I believe, the top of so the first layer is the troposphere. Oh, in fact, I think I have a picture. Here it is. So this diagram is from your textbook. And then here is the altitude in kilometers, so the altitude in kilometers. And so up to about 11 kilometers, we refer to that as the troposphere, and above that is the stratosphere. And so here, commercial jets fly maybe around here, 10 kilometers. But even if one goes up to the top of the stratosphere, I believe if you calculate the gravity, there's really only like a 1% variation. Okay? So for most common applications, we assume, and in this class, we assume gravity is constant. Okay? So then it's the density. So we now consider variations in density. So case one, the simplest case, we assume an incompressible fluid and assume the density remains constant. And certainly for liquids, which we've already discussed, it's a reasonable assumption. So we can then just easily integrate this. Rho g is a constant. We pull it out, and then we get the difference in pressure between 2 points is just proportional to rho g and the change in elevation. So here, we in general then, we would see, or what the general differential equation indicates, is that if rho g is a constant, then the variation is a constant or linear. So we can indicate that linear profile of the pressure with elevation versus P, and it would be a decreasing function of elevation. Okay? So we already have that sense that as you go up in elevation, the pressure decreases. But oftentimes, now, we're talking about liquids here, right? So an application would be, what is the pressure variation in a lake, or in your swimming pool, or in the ocean? So there, then, the question is, well, what's the pressure at a depth of? So depth, okay, we might say a depth of 100 meters. We don't say a depth of minus 100 meters. Okay? So then the coordinate, the convenient coordinate to use would be, so at the free surface of the liquid, okay, which I denote by this triangle here, okay, we have liquid body, and then above it would be likely air in the lake or ocean application. Okay? And we usually know the pressure at the interface, or at, for example, sea level. Okay? Then that would be the reference, and we may know the pressure, okay, P naught. Now, we can conveniently then define our coordinate h equal depth. H equals 0 at the free surface, and h positive going downwards. In that case, then, gravity is in the same direction. So the g vector would be positive in this coordinate system, right? So whereas dp dz equal minus rho g, okay, so with z positive upwards, pressure decreases. With the depth coordinate h, it increases with positive h. So this is positive, right? Because the original vector equation, g would be in the same direction as h. Okay, and then we can integrate from h equals 0, where we know the pressure, okay, to some depth h and p of h. Then we get p minus p naught equal rho gh, or evaluating the pressure is equal to the pressure at the surface and then increasing as you go down, plus rho gh, or in terms of the specific weight. Now, oftentimes, especially as we go into discuss pressure measurement, and as you may already know, pressure data is often given in terms of gauge pressure. That is the difference from the local ambient or atmospheric pressure, mainly because of the way the pressure is measured, that measurement device. For example, manometers work that way. Okay? So in this case, if we evaluate P minus P naught, the pressure at some depth h, the difference from the elevation or reference, which is the local ambient, and then this guy here would be the gauge pressure. Okay? So for example, at the surface of the lake or sea, this pressure might be 14.7 psi. A, so PSI, so that's pound force per inch squared. So PSIA is pounds per square inch absolute. So this is absolute pressure. So that would be this guy. So absolute. But this would be PSI gauge, or so this would be PSIG. I mean, that's one thing that's nice about the English units for pressure, because it explicitly indicates whether it's absolute or gauge. For me, in this class, if I give you a problem, I will, for example, the pressure is kilopascal. I'll either do this, absolute or gauge, or in the text, the wording, I'll indicate that that's an absolute pressure or gauge pressure, unless it's sort of obvious. For example, the 101 kPa ambient pressure or atmospheric pressure, we know that's the absolute. That's this guy, right? The textbook, I think, indicates in the text that they're going to assume, or you should know that they have the default as gauge. Okay? But I just think that, you know, for us, when we're dealing with things, we should be very explicit. We'll be explicit so it's very clear. Okay? All right. So in terms of gauge pressure, it's rho GH. Okay? But this will be our basic hydrostatic pressure equation for incompressible fluid. Now, I just really want to emphasize, you know, this is a very simple equation here, and you get in the habit of saying, okay, gauge pressure is rho GH, gauge pressure is rho GH, and it's just so easy to evaluate, you know, or even this one, P equal P naught plus rho GH. But I want to emphasize, you have to keep in mind, a fundamental assumption is that the density is constant. Okay? So I do expect you to be able to, and as we'll look at an example next of the compressible fluid, or a fluid where density varies, and I expect you to know how to do that. So the general hydrostatic equation is the one to really know. Okay? If you're going to memorize anything or really know anything, it's the general case. Then you can apply it to anything, especially as you go out in the world as engineers. You, of course, may encounter something new, different, you know, and that's how technology develops. So you got to go back to the basics. So you, as UCSD grads, know all the fundamental and general cases. Okay, then you can apply it to anything. All right. So, okay, so after this, I just have on this slide just the definition of gauge pressure. Okay. Oh, and then this is just a sample calculation, I guess I did. So let's say you do dive, or if you dive into the ocean. And so let's just look at the pressure, evaluate the pressure at a depth of 100 feet. And you can look up the density or specific weight of seawater. Okay, so it's this. And so if we do the calculation in English units, it works out to be 60 psi, and this would be A, right? Because we're evaluating the pressure. So even at only a depth of 100 feet, it is quite a significant pressure increase, of course, as you may be familiar if you do dive. Okay, so I think this, you know, I was just emphasizing here the absolute and gauge pressure units. All right. Now let's consider a case where we have density varying. Okay? And in general, gases are highly compressible fluids. And in general, liquid density is much greater than the density of gases. So if you, and you already did that in your homework 1, looked at the density difference between water and air. It's like 3 orders of magnitude. So that's something actually to keep in mind, because the variation in density, in pressure, depends on density. And so if you have a gas and you just go up, say, 1 meter or 10 meters. In a gas, the variation of density is relatively small. Okay? I mean, we don't consider that the pressure is different whether we're here lying on the floor or up on the ceiling. But if the room was filled with water and we were on the floor, we would definitely feel a difference in pressure from the top. Okay? So we actually, common, just our common daily life, we sort of neglect pressure variation within the air, within the scale, right? So in some analyses, as you'll see, we may do that. Neglect the variation of pressure through air or through a gas, but consider the pressure variation through liquid. Okay, however, in the application of the pressure variation in the atmosphere, we are going up in elevation significantly. So there, the change in Z is large. So then we need to consider the variation of pressure. And then also consider the fact that the density may change. I mean, certainly when you go up in elevation, the pressure changes. The temperature also changes. Okay? And in air or a gas, if we assume ideal gas, then the density is a function of both pressure and temperature through the ideal gas equation of state. So where do I have that written? So P equal rho RT for an ideal gas. So solving for density, then we can replace that here, P over RT. And so then we can separate variables. So put pressure on one side and then everything else on the other side. So you'll see that, of course, the G in gas constant, we're going to assume constant. And then we can consider the temperature variation as a function of elevation. Okay? And if you know that, then you could incorporate that in the integration and then evaluate the pressure variation, accounting for that. Now, the simplest case is if the temperature remains constant, or it's isothermal. So T is a constant equal T naught, that constant value. Then the integration is very straightforward to do. And maybe if you integrate between two locations, Z1 and Z2, and then the pressure, P1, P2, you can evaluate P2 in terms of P1. Okay? So that's the simplest case. But in the atmosphere, and in particular in the troposphere, so let's go back to that diagram in the text. Okay? So that first layer of the atmosphere from 0 to 11 kilometers, the temperature, so this is temperature versus altitude, the temperature in our model, the standard atmosphere, okay? So as I mentioned the other day, it is a model, a representation, a standard of how these properties vary in the atmosphere. Of course, in general, depending on where you are on Earth and what, the season and the local weather conditions, it'll vary. But for design purposes, we use the standard atmosphere. So idealized representation in Earth's atmosphere of the mean conditions. For this, it's the US mid-latitude year-round average. Okay, so you can always look this up. So this is assumed to be a linear variation, and at sea level, 15 degrees C. And then here's the pressure at sea level. Okay? And so at Z equals 0, T equal 15 degrees C, and it's a decreasing and linear function of Z. Okay? So that linear function is given in terms of beta, so the slope is beta, and that's referred to as the lapse rate, which is 6.5 K per kilometer in the troposphere, in standard atmosphere. Okay? So it's a very simple function. And again, it's a function of z, so you can just substitute that in, you integrate, and then you can get this expression for p varying as a function of elevation, where the integral began at sea level with the corresponding pressure, which was this 101.6 kPa. Okay? All right, so we have that. Now, okay, this is valid then in our standard atmosphere from 0 to 11 kilometers. Okay, so that takes care of, where did I have that diagram? That takes care of this variation. So we now have the pressure variation associated with the troposphere with the linear temperature variation. And then from 11 kilometer to about 20.1, the stratosphere, the temperature is constant. So we can go back and use that, if isothermal T equal constant, this function to represent or describe the pressure variation starting from 11 kilometers. And we would know then the temperature at 11 kilometers based on this, this model. Okay, and we would know the pressure and then also the temperature. Okay, so you can construct, at least for, this as the example here, using this temperature distribution through troposphere, stratosphere, we can use our hydrostatic equation to get the variation of pressure first in the troposphere and then in the stratosphere. Okay? Now, you should know how to do that. Okay? If you plot that, pressure versus elevation, and so this is the pressure distribution or profile with elevation, you get something like that. Okay? Now, you should know how to do that, but for future, of course, there is a table that lists properties of the standard atmosphere that you can always look up. So for a particular altitude, then you could look up the temperature, pressure, and density. And actually here you can actually see what the variation of G is with elevation. Okay, and then it even lists conveniently dynamic viscosity. Okay, so I finished that. So that's the standard atmosphere. Again, it's very simple to evaluate from our basic hydrostatic equation, the variation of pressure with elevation or height if density is constant. But I do, again, want to emphasize, you should know how to do if density varies. In general, for example, in the ocean, density actually varies not only with temperature, but with salinity or salt concentration. Okay? So if one takes that into account, things may be more complex. But I do want you to know how to deal with that if I give you, for example, some function, a relation for density as a function of depth. All right? So I told you that. Okay, now let's go now to the application of pressure measurement. I'll just set the scene here, go over a couple examples or one example, and then we'll continue next session. But so grad P equal rho G, okay, is the general equation. And so now for pressure measurement or for liquids, where we can assume rho G is constant, it is most often convenient, again, to consider the depth coordinate. But in general, we already know from common experience that as you go down in a liquid, pressure increases, right? If you go up, pressure decreases. So we already understand that. All right. So here, this is sort of the basic idea. So if you integrate this with depth, then we get our pressure difference and and linear with the depth difference. And so we get the P minus P naught is equal to rho GH if H naught is that surface, free surface, H equals 0. And then if you work this out, then you have a depth, okay, or, well, a depth is equal to the pressure difference over the specific weight, okay? And this is like a gauge pressure over this specific weight property of the fluid. And this kind of shows why oftentimes pressure values are given in terms of length units, because you could easily calculate that if you know what fluid you're talking about. So millimeters or inches of mercury, millimeters of mercury or inches of water. So if you know the fluid and the depth or height, then you can translate that into a gauge pressure. So that's sort of the basis of these types of pressure measurements. Okay? The first example would be this a barometer, which is a device, a very simple device, to measure atmospheric pressure. And so you've got essentially a container and a tube open at one end, closed at the other. And then you have this filled with a manometer fluid. Often mercury is considered. And so this thing is inverted and allowed to equilibrate. And so then you'll have some height of a mercury, and then above that, and this is closed, right? Above that, you'll have mercury vapor at the vapor pressure of mercury, okay? And that's what this is. So at 20 degrees C, the vapor pressure of mercury happens to be 0.16 Pascal, or 0.000023 psi. Very small. So small that in the measurement, one neglects that. So we know that if we start here, okay, so this would be like the starting point, and so that would be H naught equals 0, okay, and P naught is the vapor pressure, which is essentially 0, and we go down in depth, okay, and this measurement device, we can read off this height, okay. So what does this mean? Well, so now we have this pool of mercury, and so at this location here, okay, at that location, that is the same height or elevation as the free surface out here, which is exposed to atmospheric pressure. So remember, we know that in a continuous body of fluid, at the same level, the pressure is the same. Okay? So this is a continuous body of fluid, and at the same level, the pressure is the same. So out here, it's exposed to the atmospheric pressure that we want to measure. Then, through the same level and through continuous fluid, this is atmospheric pressure. Okay? And then this is P naught, which is the vapor pressure, which is essentially 0. Okay? And now we know that we go down a depth of this value, this height. Okay? And so it would be, starting with P naught, we go down this depth. Let's say the magnitude is big H. Okay? And then the pressure here, which is the atmospheric pressure, is just then proportional or equal to rho GH. Rho is going to be the density of the fluid, which is mercury. Okay? So that's why oftentimes you have the atmospheric pressure given in terms of some length or height of mercury. Okay? note on the barometer fluid. So why is it often mercury that's used? So to measure atmospheric pressure, if you use mercury, then here's the specific weight of mercury, and then you get, corresponding to atmospheric pressure, 761 millimeters of mercury. That's often quoted by or stated by weather news people, weathermen. But if one used water in your barometer, then corresponding to atmospheric pressure, the height would be 10 meters. Very inconvenient if you want to move around your barometer. So that's why mercury is used. Okay? All right, that's the barometer. We'll go into manometry next section.
It's a question for